In this video, we're going to take a look at how we can use mathematics to help us represent what's happening as a ball bounces. So, we're going to say that this ball starts on this table, and it rolls off, and it falls, and it bounces, and it continues to bounce a few more times before it finally settles down on the ground. We want to know what's happening mathematically with those values. In order to do so, we need to take a closer look at the heights of the ball as it is bouncing over time. So let's say that this table is 80 centimeters high. So if it's 80 centimeters high, we have a ruler here that can measure that. So when the ball bounces, it falls off, it has original height of 80, it hits the ground, and it bounces back up to, let's say, about 45 centimeters. So if we want to figure out what's happening here, what we need to do is make a table of values that help us track these heights as it bounces. So far what we know is that it started at an original height of 80 centimeters. And that's where it started, so that was original, so that's where we start at n equals 0. Now, a couple things to notice is that we are using this n and t of n. This is different notation than what you might expect. You might be expecting x and y. And while those still are applicable, what we're going to use here is an n value for the number of bounces. And t of n is going to be the output, and that is going to be the bounce height. So now you can see that our columns are labeled where the n is the bounce number, the number of bounces, and the t of n is the bounce height. So at n equals 0, originally we had an 80 centimeters because it was sitting up here on the top of the table. Now it has bounced once, it's come down, and it bounced up to 45 centimeters. So that is our next height value. As this ball continues to bounce, these numbers are, of course, going to be getting smaller. Now, how much they get smaller as it bounces is based upon something that's already been predetermined, and that is going to be what we consider the rebound ratio. See, we started at 80, and we go down to 45, so there is some rebound ratio which is going to be consistent for all these bounces until it finally settles. And if that's the case, I know that my next bounce, so this is bounce number 2, it's going to come down from 45 and bounce up to just over 25. So that's really hard to measure, of course, just by looking at it. It's really like 25.313. And the next bounce is going to be down to 14.238 or so. And the next one after that is going to be bounced up to 8. And we'll go one more bounce to 4.5. So if you put all those bounces together, it starts at 80, bounces down up to 45, then to 25.3, then to 14, then to 8, and then to 4.5. And then, of course, it continues bouncing, but this is good enough for us. So from here we can see what the pattern is. We already know that there's a rebound ratio. And so we can also take a look at what the graph of these values are going to look like, and you should see a pattern there as well. So I already have my graph started off here. So as I label my axes with the bounce number and the bounce height, then I can plot each of our bounce heights on this graph. Start with 0, 80 centimeters, and then 1, 45, 2, 25.3, 3, 14.2, 4, 8, and 5, 4.5. Now first, as we look at this graph, what you should notice right away that this is definitely not a linear equation. So it's not a linear equation. It does have this curve, and if you've been paying attention in class, you know that this is instead an exponential curve. And what that means is that this rebound ratio is actually also the same thing as our multiplier when we try to come up with our equation. If you remember, our equation is supposed to be the initial value, which in this scenario is 80, and then you multiply it by the multiplier to the exponent, and that's what we're going to do here. So we're going to start with t of n, which is our bounce height, which is equal to the initial value, which as we said already is equal to 80. And now we need to figure out what is our multiplier, and that goes in those parentheses to the n, right? And so we need to figure out what goes inside this parentheses, which is the multiplier, which is therefore the rebound ratio. So in order to figure out what's going on in each of these values, you're repeatedly multiplying by the same amount. So in order to figure that out, the rebound ratio, you do your bounce height divided by the bounce number. So if on your calculator you do that 45 divided by 80, what you will find is that your rebound ratio is 0.5625. So it may look like there's quite a bit going on here, but all we really did was measure the height of a ball as it bounced. And when we looked at these values, then we plotted them, we realized it made an exponential curve, not linear. Based on what we've been doing lately, you know that an exponential curve is written with an initial value and a multiplier to an exponent. So while these values might not be as simple as, say, 10, 20, 40, 80, something that's doubling, here instead you're multiplying, and what you have to do is this ratio of bounce height over bounce number to find out what it is that you're multiplying. You can always just do that ratio to find out your multiplier. And your initial value is just simply where you start, so that's that 80 right there. And so one other thing that's important to note is that in between these, we started to use an n value. And that's because in between these values, there is no such thing as a 0.5 bounce or a 1.5 bounce. That's the main reason why we switched away from using x in this spot and went towards n, because it's a number of times something has happened. So that's the n, and you can see that in the exponent up here. Additionally, because there's no information in between 0 and 1 and 1 and 2, that is also the reason why in this graph it would not make any sense to connect these points, because this happens at bounce 1 and bounce 2. There is no information in between there. So that is how we can write an exponential curve to model what's happening as a ball bounces.